So tell us a little bit about like what is, Titanoboa, and what's the objective here?
So I think there's two reasons for Titanoboa. One is that historically Vyper has not gotten as much tooling support. So people who are writing and maintaining tools support Solidity first, which is fine. Obviously, it makes sense for them. But, as Vyper people, we want to have feature parity with what you can do in Solidity. We don't want people to be coming in and being like, hey, you can do X, Y, Z in Solidity. Why can't you do this in Vyper? Why can't you do something equivalently powerful in Vyper? So on the tooling side, I think historically we have not had as much support. And that's kind of changed in the last year or two. There's more options. There's there's Brownie. Hard Hat supports Vyper 2, obviously. The other thing is that what Titanoboa enables is just, in my opinion, frankly, kind of cool. So Banteg was saying to me, wouldn't it be cool if you could prototype a Python contract and then have it be a Vyper contract? So this idea of being able to prototype and having kind of a Python kind of experience when you're writing Vyper kind of spurred a lot of the development. I kind of took that and ran with it a little bit. I was like, wait, what if you could have a Vyper interpreter? So I started implementing a Vyper interpreter. And the classic way of implementing an interpreter is this is textbook, right? Or what you learn in compilers class or something. You step through every step of the program, and then every step you just evaluate the semantics or whatever the language is supposed to do. If X is supposed to increment by 1, then you implement that in the interpreter. So that's what I started doing. I started implementing the rules for the Vyper language. And then after a couple days of this, I was like, hang on, this is this is redoing all this work that the Vyper compiler already does. We already know how to add numbers. Why am I re-implementing this? I started to take a different approach, which is we can pretend to be an interpreter. The strategy is so there's a lot of benefits to having an interpreter. You can do all sorts of things that the compiler doesn't necessarily do, or you don't get in a compiled language. The goals are very different. So when you compile Vyper code, you want the smallest binary possible. You want it to run on the EVM, and a lot of things, a lot of user-facing things are not as important. But in interpreter, you have a lot of context about what's going on, and performance is not as important. So you can do things simulate what happens on some state, or you can do tracebacks. So then the question was well, how can we get all this interpreter features without re-implementing all of this functionality that the compiler already does? And I started to go down this route of what if we just compiled the contract and then pretended to interpret it? Because we have an EVM. What if we just looked at what the EVM did and then pretend we interpreted it? And so that's what Titanoboa actually does. So and that's the entire design of Titanoboa. And in some ways it's very hilarious. It's just monkey patch the entire thing. Titanoboa is this generalized execution environment for Vyper. After I got the initial Titanoboa implementation working, which is it uses PyEVM, which by the way is quite a nice library, I realized that you could start overriding a lot of PyEVM functionality, and you could start enriching it with stuff you would like to know about Vyper. I think one issue people have a lot of issues with when they're developing smart contracts is it's kind of hard to debug them. Your program reverts or fails with execution reverted, and you're why? So one constraint in the Titanoboa design is that it's pinned to a specific Vyper version, and that's a trade-off. So you can't compile Solidity code with Vyper. You can't compile old versions of Vyper code with Titanoboa. But what that allows you to do is it is able to take a lot of the compiler internals and make really convenient UX. Titanoboa now has like, since I work on both Vyper and Titanoboa, I added these error maps into Vyper. So like a lot of issues are like with compiler generated reverts, like safe math, or like auto reverting on when you like call a contract and the call fails. Vyper now generates reasons. And so like if you have the opcode or the PC where like some transaction failed, you can actually get the reason for why the compiler, like some compiler inserted check and why it failed. And so like now Titanoboa like shows you that. And it also enriches failures with like stack traces. So they're like Python style stack traces. You see, it kind of looks like a Python stack trace when stuff reverts now. So like you can see the entire history or like call stack of like why stuff failed. Also and then once you have this architecture, you can start doing kind of cool things because you're not restricted by RPC anymore. So the way all these frameworks work, like Hardhat, Truffle, Brownie, and I was thinking about Foundry, and Foundry is different because it kind of gets around the RPC problem by having a special VM and having these cheat codes and stuff like this, which in some ways is conceptually similar to what Titanoboa is doing. So once you're not restricted by what the RPC allows you to do, you can start instrumenting your execution at a very fine-grained level. So one example is like in Titanoboa, the SHA-3 and SStore opcodes are like overridden. They're like patched. So they like do something that's not exactly what the PyEVM implementation does. And what they do, which is besides what the PyEVM implementation does, is it doesn't mess with the EVM semantics. But what it does in addition to what PyEVM does is it traces them. So like on any execution of a Vyper contract, you can actually enumerate mappings. So like mappings, the keys are like normally erased at runtime, but in Titanoboa it traces all of them, and so like you can access it as like a Python dictionary. So you can do things like check that the entire like you can do things which like test what the entire contract state is before and after some code executes. So another thing you can do in Titanoboa is like eval arbitrary Vyper code, which is something that you kind of expect an interpreter to be able to do. And the way that works is by like, again, pretending to be an interpreter, it like compiles the code. It actually runs the Vyper compiler. So it actually semantically analyzes and compiles the code using Vyper as a library, and then it runs it using PyEVM. There's also line-by-line gas profiling, which somebody asked me for, a week or so ago, and they're like, it'd be really cool if, we could profile every single line and see where the hotspots are. And so now you can do that with Vyper and, Titanoboa, and it'll show you like where the hotspots are, and there's different ways of sorting the profile. Other things you can do with this architecture are like in Foundry, there's like cheats, right? There's ways of interacting with the outside world that are not part of the EVM. And in Titanoboa, you can actually go one step further and like define your own cheats. And you can do this by just like registering a precompile with PyEVM. And with this, you can do like lots of different things. You can interact with the outside world. You can interact with the file system. You can, like, let's say there's some complicated function that you need, like some math function, like natural log, or and you don't already have an implementation in Vyper because it's maybe difficult to implement. What you can do is like you can register it as a custom precompile, so it's like not a blocker, and you can like work on other stuff, or like maybe work on stuff in parallel with somebody else until that particular piece is done. And you can, stuff that I end up having to do in order to like implement functionality is like, you can kind of modify the virtual machine on a very fine-grained level. So like, let's say for purposes of simulation, you want to like mark storage slots as cold. Again, you can do that. The way to I implemented forking, so you can fork mainnet with PyEVM now, or any RPC really. And the way to do that is like just to mess with the specific internals of PyEVM that are related to like getting and setting accounts in storage. And so like it's strictly more powerful than RPC, because anything that you can do in RPC you can do with Titanoboa, but you can also override anything you want in the VM. So like it's really gives the user a lot of power to like modify how stuff is executed.
Mm-hmm. Yeah, Josh and I were talking before this, and I really think more people should follow your work on it on Twitter, right? So we'll let you plug your Twitter handle here in a little bit. But yeah, I mean, I think the community is going to really appreciate this as it continues to get rolled out. So keep up the good work with it.
Yeah, and the other thing is it's an embedded EVM, right? So you don't need to spin up another node to run your tests. So this makes multi-threading work. So like if you want to spin up a million cores, run, some tests over, you can do that, and all of them are running their own EVMs, right? And so because it's all in process, you get fairly easy access to like any Python functionality. So like you can just use PyTest, and that like gives you a lot of functionality right there. Like there's PyTest xdist, which is like parallelizes your tests automatically. There's like PyTest hypothesis, which is like a very general fuzzer, and you can do like fairly complicated things with it too, like different strategies, which maybe we could expose more cleanly in Titanoboa, but you can implement something very similar to Foundry's assertion invariant testing. Like I said, you can do anything in Python with it. So like in order to like configure your tests, you can like run arbitrary Python code before like you enter the Titanoboa execution. Or you can like, using user-defined precompiles, you can actually like have two-way bindings between Vyper and Python. So you can like interrupt your test or interrupt your Vyper code, do something in Python, and then come back.